Okay, welcome everyone. Uh, on Wednesday, last week, we start to learn X-ray. Hope you still remember. And let's have a quick recall about what we have learned now. Um, X-ray is a kind of electromagnetic radiation. I'm sure all of you knows this. And then the wavelength of the X-ray is between 0.001 to 10 nanometer. But normally we regard X-ray is about 1 angstrom. That's because the X-rays came from copper is about 1.54 angstrom at the K alpha 1 line. Okay, so you can regard X-ray about 1 angstrom, something like this. So how do we generate X-ray? We use gas discharge tube. As you can see, this is a modern X-ray tube. Modern X-ray tube include metal anode, and you can use any metals like copper, tungsten, or others, moly. And then it includes hard cathode. Hard cathode is the place where generate electrons. And if you have a voltage potential differences, then electron beam will shoot from cathode to the anode, so that we can generate X-ray from the anode. And because you need to have a high voltage or you need to have a high energy electrons, so you need to apply high voltage between cathode and anode. And in order not to let electron have interactions with the molecules in the air in the gas phase, so this tube require high vacuum condition. So this is the how are you going to generate X-ray using X-ray tube. And once X-ray generated, there are two type of spectrons. The first spectrum is called characteristic X-rays. And as you can see, this is called characteristic X-ray. Every different metal has its characteristic X-ray. For example, I just told you that the copper K alpha 1 line will be 1.54 angstrom. Okay, so they can generate K alpha, K beta, many different lines, many different energies here, with different wavelengths, of course. And this is a case of the moly at 35 Kelvin, 35 kilovolt. Okay, so this is what we call characteristic X-ray. And another type of X-ray is called Bragstrom continuous X-ray. Bragstrom continuous X-ray is this is Bragstrom continuous X-ray. So there's a kind of energy exchange from the electrons and the atoms. Okay, so and this is not quantized. The energy is not quantized. So this is Bragstrom continuous X-ray. And in the end of this energy, which is the highest energy, and we follow Duhem-Hunt's law, we can find out the energy or the wavelength, the highest energy or the shortest wavelength using Duhem-Hunt's law. Okay. And final information we want to know is the application of X-ray. As you know now, X-ray used in many places. For example, medical X-ray. So if you go to a hospital, you have X-ray check. Okay, and if you go to airport, you have security check or security inspection to avoid you have knife, you have gun, you bring this kind of forbidden items to go to the airport, to go to the airplane, right? And also X-ray can also identify elements. For example, we have an example show you that EDX, WDX, and XRF. Okay, so this is what we learned last week. And last week we also learned X-ray diffraction. There are two types. The first type we call Lowy diffraction. Lowy diffraction means what? Means the X-ray transmit to the objects, and you find a pattern behind your objects. So that's what we call Lowy diffraction. Another type of diffraction is Braggs law. We call it reflection. So the X-ray can transmit to the object, but also can reflect from the object. So you got two types of patterns. The first one is Lowy diffraction pattern. The second one is de Broglie a pattern by refraction, and we follow the the Braggs law. Okay, so that's what we learned. And I hope you still remember Lowy diffraction. This is Lowy diffraction, and we have fold. Okay, the equation of fold is equal to 360 degrees divided by base angle of the rotation. If you rotate this plane, and once you rotate and you return back to its original, it returns to the same shape. And this is, for example, if we change this, if you rotate this in the from the center, and you got 90 degrees, and you will be the same shape, and the basic angle of the rotation will be 90, right? So 360 divided by 90, that will be what? That will be 4. That will be 4. Now 4 means what? 4 means you are looking at 100 plane from this way. So this is 100 plane, and the X-ray beam shoot from this direction. Okay, and this is 110. Okay, this is 110 is 180. So the fold will be 4. The fold will be 2 here. Okay, then this is will be 120. So the fold will be equal to 3. Okay, so you need to remember this, and I hope you remember. If I give you a pattern, something like this, I ask you how many folds in this picture, and you need to find out. Okay, and the second topic of the diffraction is diffractometry and using Braggs law. So interference, one is constructive interference, second is destructive interference. So interference, you have two, and we focus on constructive interference, and this is Braggs law. And ladies and gentlemen, I want you to remember this equation. Why? Because n lambda equal to 2d sine theta. M is an integer number from 1, 2, 3, 4. Lambda is what? Lambda is wavelength of the X-ray. So you know this because if X-ray, the source of the X-ray is from copper, that means that normally we use the lambda will be 1.54 angstrom, right? So you know this. And 2, of course, and d is the d spacing, the interplanar spacing of the planes. So this is d. Sine theta is what? The angle of the electron beam which shoot from outside to the object. So you know the angle. So the only thing you don't know in this equation is this one, d spacing, interplanar spacing. So that's why you can find out the d spacing according to this equation, Braggs law. Okay. So today we start from here. So Braggs law, we know that this is equation, and you can obtain DHKL from these 3 numbers. So once you have different faces, face to the X-ray, you will have different patterns. You can find out different d spacing. Okay, So for the case of the cubic crystal structure, you need to know the H length and the atomic radius, right? And also the D. So because for the cubic crystal structure, A equal to B equal to C. So this ABC is equal, and D is interplanar spacing, and then HKL is the Miller indexes. You know that? And Miller index, the D is, you can follow this equation. I hope you still remember. So the relation between D spacing and H of the length, this equation represents the D spacing and the H length, right? And you also know the H length depends on different crystal structure. You know A relationship between A and radius. So there are three numbers: D, A, and R. R is the radius. Okay, so you can play this around. Once you know the D, and you will know the A. Once you know the A, and you can find out the R. Or once you know R, you can go to the A and you go to the D, something like this. So for example, if we have D10, that means what? This is the plane of D110, parenthesis 110. So you know this, and using this equation, you understand this. You find out the relationship between the D and A, right? Okay. Right. So this is another type of fingerprints of the crystal. Why? Because this spacing will be always different. Depends according to different type of the metals. Okay, and because the size of the atom is different, and this spacing will be the difference. It also depends on the type of metal, but also depends on the phase, the planes, X-ray, you face to the X-ray, right? So this, what we can say, is a fingerprint of the crystal. So what's the fingerprint of fingerprint of electron? Anybody want to tell me? Fingerprint of electron. 0.5 points. Yes, early bird. We have less students today because of weather, right? Because too cold. Yes, please. 光谱残念ですね。No, it's not. That's another type of fingerprint, but you can raise your hand. Fingerprint of an electron. What's the fingerprint of an electron? You know this, right? Yes. Thank you very much. Quantum number, right? Quantum number is, there are 4 quantum numbers. This 4 quantum number can represent what? Electron. An electron. Every electron is individual, right? The quantum numbers. Okay, so I want to ask you another question. Spectrum, light, I can say electron radiation spectrum or light spectrum represent what type of the fingerprint? Anybody want to tell me? Did I explain this clearly to you? Yes, please. Yes, that's the generation of the spectrum. But what I want to ask is, this fingerprint represent what kind of the spectrum fingerprint represent what? For example, quantum numbers represent atoms. Oh no, I said quantum number represent electron. So what the spectrum represented? Yes, that's right. You know, if you put different atoms in the gas discharge tube, you got different spectrum, right? So the fingerprint of atom is spectrum, right? Okay. Right. So what's the fingerprint of the crystal? X-ray diffraction. Okay. Right. Thank you. So interference of and criteria of and the process of crystal structure. For example, if you want to find out this is a D spacing, you want to find out this structure is FCC BCC plane, so you can use X-ray diffraction. Why? I'm going to tell you very soon. Okay, so why the fingerprint of the why X-ray XRD can represent the fingerprint of the crystal? Because if you do this process, you can get a set of expected reflections, a set, not only one, a set. Okay, so this a set of expected reflection represent the fingerprint of a crystal in what phase. Okay, I'm going to tell you very soon. So let's have a quick review of X-ray to determine X-ray crystal structure. Okay, so this equation came from this distance, the actual distance traveled by wave 2. This is wave 1, this is wave 2. And this is the actual distance traveled by x2, wave x2, wave 2. Because, this wave 1 travel this way, wave 2 travel this way. This is actual distance. And if you want to have a constructive interference, this wavelength, this actual distance need to be what? Need to be an integer of a wavelength of this X-ray, right? Okay, so that's why we find out this is the equation. The measurement of the critical angles theta allow computation of planar spacing. So you will change this theta all the time, so you can get a set of the a pattern. Okay, you can get a set of the X-ray, constructive X-ray. So for example, this theta, if you shoot the X-ray from this way and you have an angle theta, and you got constructive interference. So this figure show you that in x-axis there's a theta here, and y-axis is the intensity from the detector. You have a detector here. So if we have a destructive interference, you got nothing. If you have a destructive interference between these two beams, you got nothing. So intensity will be 0. But if you have a constructive interference between these two waves, X-ray, you will have a peak here. You will have an intensity, right? Right. So if you change the theta, you will find some place has a peak, some place has no peak. Okay. So this is how we determine the crystal, by changing the shooting angle. And we understand because of intensity, you can find out the D spacing using this equation. Okay, so in contrast, the non-constructive interference showing nothing. So you have a very low intensity of the diffraction beam, and you got nothing. However, in the previous case, we are only talk about this case, the body center, the simple cubic structure. We haven't talked about face center cubic and body center cubic because it makes things a little bit complicated. So it's not the scope of in this lecture, so we will skip this. But let's take a look at this explanation. The Bragg law is only for unique cell having atoms positioned at the cell corner. That's Bragg's law. This equation only applies to this. So the Bragg's law is a necessary but not sufficient condition for diffraction by real crystals, because this is only one case for the metal, right? This has many cases. So situate at the other sites like FCC, like corners, center or face, as the extra scattering centers, which can produce out of phase scattering at certain Bragg angles. So the net result should be represented with consideration of specific crystal structure. So it depends on different crystal structure, you can get different pattern, right? This is how we explain to you. So that with different structure like FCC and BCC, for example, the iron at room temperature is BCC structure. So you got one type of pattern. If we increase the temperature, go up to 900 or 1000, the FCC become BCC. The BCC become FCC for iron. So at that temperature, you got different pattern for iron. Okay. So thanks to Bragg, actually is a father and son. They got Nobel Prize together because of Bragg law, because of X-ray diffraction, and he's the youngest Nobel Prize winner in physics. When he got the prize, Nobel Prize, he's the age of 25. He should thank his father, right? Because his father got Nobel Prize. He's young to get Nobel Prize, but he's not the youngest. The youngest is who has the age of 17. I got Nobel Prize in a Nobel Peace Prize, okay, in 2004. But she's not from scientist part. She's from the, another part of the Nobel Prize. Okay, so because this idea, this innovation, this kind of great achievement is made by Bragg's law, Bragg's father and son. So you can write, normally Bragg's law, Bragg's law, in regard to 2 or 1. That's okay. That both okay. Okay, now let's take a look of the diffraction techniques. So this is called X-ray diffractometer. So you put your unknown materials into this XRD machine. Okay, and this is we call X-ray source. X-ray shoots from this place. The X-ray beam here. And of course, you have an angle. That's for sure. And this is a specimen. You put a specimen here. And then you have a collector or detector. You detect, if it is constructive interference, you got high intensity. If it's destructive interference, you got nothing, right? So this detector can move. You show the different angles. So this 2 theta, this theta, this will be 2 theta, right? Okay, so this axis around which the specimen detector rotate. So this one will rotate. Instead of detector rotate, no, you don't want to rotate X-ray source, right? It's not practical. So you rotate this one. You change this. You change these angles. The stage will change the angle, and then this collector or detector will move to detect the signal from here. Okay, so and then you got a set of the pattern. So let's take a look at this. So this is what we call powdered X-ray diffractometer. So you put powder here. You put powder. Powder is there are many small grams, single crystal gram, right? So specimen is powdered or polycrystalline grams. And the character of this powder or polycrystalline gram is very small, fine, and the randomly orientated particles, because this phase might be 111, and the same place this phase might be 100. So that you can show up many different phases on the surface and randomly distributed. So random orientations, right? Random orientations ensures that some particles are properly orientated. Every possible set of the crystallographic planes will be available for diffraction. Okay, and then of course we require X-ray to be the source of X-ray to be a monochromatic X-ray radiation, right? single, strong, and coherence. So the collector moves at a constant angular velocity. A recorder automatically plugs the diffraction beam's intensity. So important thing is that the collector got a signal and plug out for you automatically. So now the technology is quite mature but expensive, of course. The machine is expensive, but you can get the information very soon and very quick and very correct. Okay, so CEDA is different from the CEDA in the Bloch's law. So this 2, right? We should say 2 CEDA. Right, so now let's take a look of an example. It's called diffraction pattern for powder leads. The powder leads, you can if you think of the powder, you have powder means what? Very, very small grams of the particle together, and it looks like this. And lead is black, of course. And so you put this powdered lead to the stage, and then diffraction beam intensity is a function of 2 CEDA. So if you have 2 CEDA here, this is the function, right? So if you change, you got different intensities. So as a result, you can plug something like this. This is normally start from 10 because 0 is impossible, right? So you start from somewhere here, okay? This is 2 CEDA from 10. 10 is also small angle. It's not practical. From 20, that will be 10 to 20 and up to 9, something like this. Okay, so in high intensity peaks resolve when the Bloch's diffraction condition is satisfied by some set of the crystallographic. So in case of powder lead, if you get a pattern something like this, you might get some pattern something like this. So you do the scan from, let me show you again. If you do the scan, and you will get peaks. This is characteristic X-ray. That means that this 110 means that lead we already unknown. Sorry, it is known metal. So if you go and check the database, this database will tell you that these peaks. First, let me restart. If you get a pattern like this, the first thing you need to find out is you need to identify what kind of machine, what kind of metal, unknown metal is this. Okay, so you put this pattern to the database. Computer will analyze for you and tell you, wow, this is a lead metal, or this is a gold metal, according to them. And all this is information 1. Information 2 is the machine or the computer will tell you that this peak represents 111 plane of the lead. This plane represents 0200 plane of the lead. Okay, so this is the phases, the planes of the lead, which the X-ray detector can receive the information. And as you know, the plane 111 has highest density. That means what? That means this plane is small compared to another, right? Okay. So this is what we call quantitative analysis, not qualitative. Qualitative tell you that this is 111, this is 200, and this is lead. This is qualitative. Quantitative tell you the number, the comparison, high and strong, low, something like this. Okay, this is one of the example. So normally you get a set of the X-ray and patterns. So for example, you got a pattern like this, and you don't know why is this. You don't know why is this. So you take this data and ask computer to analyze for you. And computer tell you that, wow, this is iron, alpha iron, BCC. Thank you for the computer. Now it's very powerful, In the old time, it's not like this. It's not as easy like as this. Anyway, and then not only this, computer will also tell you, wow, this is 110 plan of the ion. And you know 110 of the ion is, this is BCC structure, right? So this is 414, and this represents ion. And this is 110 phase, or 110 plan, which is this one. So this peak represents the plan, and this one 200. And we understand, if I want you to draw Miller index of 200, I'm sure now you can draw, you can tell me 200. And how about 211? This is to represent 211. Okay, you know the 211. Okay, so this is very powerful tools if you have the unknown. Not only metals, but also ceramic. Okay, but also any other crystal structures. X-ray can find out. So this is how it looks like, X-ray reflectometer. So you have a detector, you have X-ray, so and you have a stage for you to sample. I want this, but I don't have money to buy. Okay, please donate me. Okay, these days, you know, the politician always ask you for the donation. Okay, if you want to donate me, you are very welcome. Okay, so diffraction techniques. The technique of diffraction is X-ray diffraction. This is more powerful than the Laue diffraction, because this qualitative and quantitative chemical identification. Not only it can tell you the metal, but I will show you how powerful is this tool. So crystallography orientation. So they can tell you the chemical identification, but also tell you the crystallography orientation, like 111200. Okay. And also, this technique also can tell you the crystal size and the residue stress. Crystal size means this one. If you have a powder, you are quite curious about the size of the powder, especially if you cannot observe the size of powder by your eyes. You need to get help from microscopes. But if you don't have microscope, X-ray is kind of another tool, can tell you the size of the powder. So not only X-ray can produce diffraction pattern, but also electron can produce diffraction pattern. As you know, electron can behave like a wave as well as particle, right? So as long as the wavelength of the electron and also the gap between atoms are quite equal, are similar, so you can produce electron diffraction pattern by electron beam. So not only X-ray electron, but also you can have neutron beam diffraction. No charge, right? Neutron beam. So data analysis of the X-ray diffraction is that the identification of a sample. For example, you got a pattern like this, and then you go to check the database. I just give you a website. It's called JCPDS, and you can, you know, in the past we need to buy this, but now it's free. Thanks for the internet. You know, everything is quite good, quite useful, and quite powerful, quite fast. And then you can realize what is this material. Okay, and also you can determine the Bragg law from the angles, right? So you can calculate what, according to this, you can calculate this spacing by if you have a peak, and you can calculate this by what, this spacing or interplanar spacing, and after interplanar spacing, you get this, you get D from this equation, right? And after that, you got A from this equation. So you can get D and you can get A. And also, later you can get what? You can get R right? You can get R, radius. And I'm going to show you another equation called Schiller formula, Schiller equation, to tell you, to determine something. Okay, the particle size. Right? So, are you with me so far? Are you with me, right? Good, good. Okay, so data analysis, D spacing and A, I just told you, and this is not difficult at all. If you have a gold, you don't know this is fake gold or this is expensive true gold. So you just take this gold and to do the X-ray analysis, and you got a set of pattern. And this set of pattern tell you that, wow, this is true gold, expensive gold, or this is fake gold. You don't want to spend too much money on this. Or it also can tell you if you put copper, 50% copper and 50% gold into this brick. And you also can find out by X-ray diffraction. And X-ray diffraction tell you, well, this is not 100% pure gold. This has some impurities like nickels, like coppers. And so you don't need to spend too much money to buy this. Okay? Or you can, of course, there are some golds contained inside, but you don't need to spend too much money. So find this spacing for 111 planes and the distance constant A of the gold. So can you do this for me? Of course you can, because this will be in your final exam. Please. Right. So the information I will tell you is that what's the wavelength of the X-ray? Of course, I need to tell you. So the wavelength normally is from copper. So copper K alpha 1, which is 1.54 angstrom. And if you know this information and you know the angle, so if you know the information, you know the angle, you can let's set as 1, 2, or 3. Of course, you make sense to you whether it makes sense of the D once you put 1, 2, 3, 4. But you use 1 first here. Okay. So you put a number because this is 111, right? You put a number 111 here. So you got what? You got D according to wavelength and theta. Theta is here, right? 38.3. However, you need to divide by 2 because this is Bloch's law angle and this theta is 2 theta here. So you need to divide it by 2. 38.3 need to divide it by 2. So as a result, you can find out that the D will be 2.35 angstrom. And once you find out D, then it will be easier for you to know the A. Once you know A, it's easy for you to know radius of the gold. If you know gold in room temperature is BCC or VCC. Right, this is a kind of practice for you. Please try to do the calculation for yourself. And I just want to remind you, in your final exam, please bring your calculator. Celebration of learning. I'm sorry. Celebration of learning. Right. The good thing is that, as I told you, that if you have if you have a piece of gold, and somebody want to tell you, well, this is 100% pure gold. Do you believe this? Or you feel that this piece of metal must have gold and other elements, for example, coppers or nickels, for example. You don't know. So you put this piece of metal or alloy to the X-ray machine. X-ray machine tell you that, well, this not only has contain gold, but also copper, silver, something like this. So XRD patterns of silicon is a kind of example to show you a mixture of the X-ray pattern. So here there are 3 powders. There are 3 types of powders. The first one is called glass. Glass is amorphous silicon dioxide. Okay, and as you can see, this SF doesn't pack in order. Okay, so this is we call amorphous silicon dioxide. And another tool represent here is a crystallized silicon dioxide. So this amorphous silicon dioxide, this is what we call crystal bullet. Crystal bullet, another one type of the crystal XiO2. And the quartz, I'm sure you know that this alpha quartz is another type of crystal silicon dioxide. So these are crystal. This crystal. We put these three type of the powder together. So we got a pattern something like this. We got a pattern like this. So say, well, Professor, is this Brustronham curve? No, this is not Brustronham curve. Okay, Brustronham curve is law is not, we cannot represent here. This is not Bragg law. So actually, this is a combination of three peaks, three type of materials. The quartz here, if you have a pure quartz X-ray, you got peak like this, pattern like this. If you have a pure crystal bolide powder, you got pattern like this. If you have a glass which amorphous, there's no peak. It's kind of broad band, broad peaks. So there's no characteristic peaks here. So once you have amorphous peak, once you put amorphous materials to the X-ray diffraction instrument, you got nothing. So the combination is like this. Okay, so now the computer can easily use this peaks, this pattern, and to divide or to fit different elements into this pattern. So it's easy for you to analyze the combination of the elements, which is the mixtures. Okay, so the mixture will be equal to what? The pattern of quartz and the pattern of the crystal bullet and the pattern of what? The glass. Okay. So this is another example, is that if you got pattern like this, and you can identify this material include alumina oxide, okay, and the cobalt. It's a combination of these two. And also, if you found that the peaks is a strange, there's a shoulder of the peak, and this might be a combination of the two peaks, of course. And you, according to your experience and according to the power, how powerful is this computer, and you can find out of how powerful of this software. You can find out what this peak represent gallium nitride, and this peak represent indium gallium nitride. Okay. So X-ray diffraction also depends on the pressure. So if you have, as I told you that if you have a metal, iron metal, and at room temperature you got one type of structure. At higher temperature you got another type of the structure. Of course, you get different patterns, but also the pressure will give you different X-ray patterns, even using the same material. So this is the zinc sulfide structures of the pattern, but this is under the 4.9 gigapart. This pressure, very strong pressure, and you get patterns. Because of what? Because crystals, the packing of structure is little bit different. Okay. So I hope you still remember I told you that X-ray diffraction pattern not only tell you the quantitative and qualitative analysis, but also tell you the orientation of the plant, or orientation of the crystal. And next topic will be how to determine the crystal size, the size of this single small grains. How do you determine this? And that's what we call this is the story we want to talk about, Scherer equation. Okay, so next topic is also important, and this will also be in your final exam. This will be in your final celebration of learning. It's called Scherer equation. And Scherer equation is to use for the determination of crystal size. So he is Scherer. And the diffraction, the X-ray diffraction is a convenient measure for determining the what? The mean size of the single crystal nanoparticles, or the crystalline in nanocrystalline bulk material. Anyway, you just need to decide the crystal size. So he's a Scherer. He found this is a Scherer equation, and because his professor is Debye. Debye is also another famous scientist. Anyway, you don't know him, but anyway. But some people call this Debye-Scherer equation. Actually, it's not. Scherer, he is the one who found. He don't has the equation has no his professor's name, unfortunately. I want his name. I want my name on there if my student make this equation. But anyway, this is out of story. This is not the very important thing. But so if there's no Debye-Scherer equation, only Scherer equation. Okay. Right, ladies and gentlemen, I want you to remember this equation: D equal to K lambda divided by B cosine theta. This is not difficult, but you might find, well, Professor, how can you decide this equation? I don't have time to tell you this, and you can check the book. But some of them is from empirical. This is kind of empirical equation. So D is the mean size. So you need to decide the means. You need to decide the size, right? D equal to K, the dimensional shape factor. So K is a kind of shape factor. And normally you use 0.9. So in your final exam, I'll tell you D. K, I will tell you K. Can be 0.9, can be 0.85, 0.87, for example. But varies with the actual shape of the crystalline. So this is K. And lambda is the wavelength. Of course, we know that normally we use the wavelength of lambda is 1.54. Okay? So no problem with this one and this one. How about beta? Beta is the light at half mass intensity. What does that mean? Light broaden at half maximum intensity. Or here we call full width at the half maximum intensity. Let's read this first. After subtracting the instrument light broadening in radian, okay, in radian, not in degree, in radian. This quantity is also sometimes denoted as a delta 2 theta. You can calculate it. You origin software. You can calculate in software, or you can use ruler actually. In your final exam, just simply calculate this one. And theta is what? Theta is the Bragg angle in degree. So this is radius. This is degree. Don't mix up. Okay, don't mix up this one and this one. Okay. So the important thing here is because a part B, all you want to do is put a number here. If you know this, you just put a number in and you can find out. What about D? About B? B is called FWHM. So if you have a peak here, and then this is the intensity, the maximum intensity, and the half of the intensity is this. This is half intensity. If you the highest, right? If you divide this by 2, that will be half here, and half, and then this is half maximum intensity. The broaden full width is from here to here. So this is x2 divided x2 minus x1. x2 minus 1. Okay, so this is the number here. You need to put it here. So there are two steps. The first step, determine the highest peak, and then divide it into 2. So you know the half maximum intensity. And then step 2 is the maximum intensity, the half maximum intensity go to x, and you got the number of a degree, and you subtract the degree x2 to x1. Okay, you got the answer. And put it here. Right, so full wise at half maximum is called FWHM. Is blah 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 blah. Anyway, please read this. But what I want to tell you is highest the peak divided 2 and subtract the numbers from x-axis. We are going to have it. Now this is x2 subtract x1. So for SRD, Scherer formula, B is the differences in angle at the half maximum. So this is a key in this equation. Others, you just put the number. You just put the number in. Okay. So if you want to do the computation, you need this anyway. So what does this equation tell you? If this peak is broadened, is increased, is like this, that means x2 plus 1 is high, right? Then diameter will be what? If it is high, the diameter will be small. Okay? So if you have a broadened peak, that means the particle is small. If you have a sharp peak, that means the particle is big. So let's take two examples. The smaller crystals produce broadened X-ray diffraction peaks. So once you get this large gram, single gram, you got very sharp peak. So if you have small grams, you got what broadened peak. So this is an example to showing you that this is zinc oxide. Narrow size zinc oxide, you know that the peak is broader. And but micro size zinc oxide particle, the peak is sharper. Compare I should say the peaks are all sharper, right? Not only one, but also others that they are all sharper. So when to use Scherer formulas, Scherer you cannot use Scherer formula to a bulk particles very big like millimeter or centimeter. So the crystal size need to be less than 100 nanometer. So normally it's about 100 to 200 nanometer. Okay, so this is the equation to calculate the particle size, but also the peak broaden can be occurred by other factors. So this Scherer formula tell you that the size, the shape of this, the broaden of this peak, it can decide the size of the particle, but also the strength, and the instrumentation will also influence the size, the peak's broadening. Also, the solid solution in homogeneity. We are going to talk about solid solution in chapter 4. Okay. So and also the temperature will also affect the peak broadening. So if the brace consistence for each peaks, I mean 5 peaks, and the brace the size change is consistent for each peak, then assure the broadening due to the crystal size. Okay, so in order to this is roughly idea. You need to analysis or need to determine is that if the brace is consistent, and the factor might be the crystal size, not the instrumentation or not the temperature or not the pressure. Okay, but this is not correct. In order to find out crystal size, you can check the XEM. You can use microscope, electron microscope to find out. It's not exactly to need to know this. So this accuracy is about 20 to 30%. This is another example to show you that the diffraction peaks position and wise. There's no strength, but if you get a strength to this material, the peak will shift the angle. Okay, and if you give the strength not uniformly to this material, for example, if you bend, so the strength is not uniform, so you got a broadened peaks compared to this one. So this is another example to show you that there are many factors to affect the size, the peak broadening. Okay, one of the factors is crystal size. One of the factors is strength. Another factor might be temperature. So, and instrumentation. If your machine is not good enough, so if your machine is very cheap and not maintained well, so the peak might show you like this, and you might misjudge the analysis. You might misjudge the materials because the true peak becomes if you have a good machine to do the analysis. But this information was hidden because you don't have a good machine to do the analysis. Anyway, this is another story. So here I want to show you an example. So please work with me. Schiller's equations. So this is a gold foil. This is example of gold foil. This is the angle, and this is the intensity. And if I want to ask you, please pick up the highest peak in terms of intensity, the highest intensity peak, and then to find out, use the peak to find out the crystal size. And you know, if I show you there are only two peaks in this region from 95 degree to 99 degree, and you got this. You got this peak, right? So the 98.25, and the plane is 400. So first of all, if you use this equation, and I will tell you the K is 0.89, not 9, it's 0.89. Okay, and I also told you that the X-ray, the wavelength of the X-ray is copper, K alpha 1, which is 1.54 angstrom. So you put this number here. And I also tell you the angle, right? 98.25. So you can put the angle here. So what you need to know is what? Beta, B. The B is what? Half intensity or what? The distance between this. So B is what? B is, if you use ruler and you cut this in half. Of course, I don't. I will give you a better number. Okay, you put it here and you find out. Well, this is 98.3. This is 98.2, and you 98.3 divide minus 98.2. Okay, you take this out. And you put the angle here, and you got the number. So again, you put the number back to this equation, and theta is 98.25 divided by 2, right? Okay, so you put a number here, and then this is right, and you got the particle size is 120 nanometer. Okay. Good. So be careful with this and this. This is angle. This is, okay. Right. So this is a very simple way to find out the particle size, but with the accuracy accuracy of 70 to 80%. Right. So let me summarize the X-ray diffraction and patterns. The X-ray diffraction is the compound analysis. You can find out iron oxide, iron Fe2O3, 3O4, and this kind of materials. Or you can have a compound, right? Compound, as I told you, like amorphous silicon dioxide and the quartz silicon dioxide. And of course, this tool is not for amorphous materials. It's only because of the Bragg diffraction, right? Diffraction pattern. Amorphous material doesn't generate diffraction pattern. So unfortunately, you cannot use XRD for amorphous materials. And also, this is qualitative and quantitative analysis. You got the intensity. You can analyze the amount of the aluminum oxide and the copper. And another tool I showed you last week is X-ray fluorescence, XRF. XRF is for element analysis. So if you put this oxide to the XRF, the XRF will only tell you, wow, this object or this substance only has the element of iron and oxygen. It doesn't tell you this material is iron oxide. It cannot tell you this is Fe2O3 or Fe3O4. But XRF can tell you. Okay, but good thing for XRF is that you can have the amorphous content evaluation. That means it can tell you, do you have oxygen, you have iron. Okay. So this is summary. Okay. So let's go. Is in the final stage of the non-crystalline solid, section 3.17. So non-crystalline, or also we call amorphous. This is crystalline material, right? This is non-crystalline. As you know that it doesn't pack in order. So this is an example: silicon dioxide crystal and the non-crystal order, disorder. Right. So in chapter 3, we only talk about metal. Why? Because metal is only contain one element, which is the simplest case for us to start with. But for the ceramic has two, including two elements to 3, 4. So it will make structure more complicated. However, we also follow the same rules, right? Some of them are crystalline solids. Okay? Some of them are not, like inorganic glasses, which is amorphous. And polymer also has a crystalline material and non-crystalline material. Okay, have you heard about liquid crystal? Liquid crystal, right? Liquid crystal is a kind of crystalline polymer. Okay? Right. So, I think I finished the section 3. So, Friday, we are going to start chapter 4. Okay, chapter 4 is called imperfection. So we start to introduce the foreign elements into the main materials. Okay, that's called imperfection. Right. Okay, I think that's it for today.